let's look now a little bit more at some different topics that can cause color in ceramics. So the first bullet there that we talked about was transition metal ions. Now we're going to talk about some other means that we summarized above. Okay, but first let's think back to a topic that we looked at a little bit. So we talked about how if we want a highly reflective surface is required, we talked about the relation to index of refraction. So choose a material that would give us the highly reflective surface. One material with a high index of refraction or one with a low, and then see if you can explain that connection. So pause the video, come back, and we'll talk through that. Okay, so again, just in case you're just looking through the slides here, I wanted to draw your attention to what we're talking about. So again, we talked about the highly reflective surface. And so for a highly reflective surface, we saw that that was related to the index of refraction. In particular, it needed a high index of refraction. So if you don't remember this part, go back to the previous lecture and we made the connection between a soda lime glass and a leaded glass, where that leaded glass had a higher index of refraction and therefore it had that sparkle or that highly reflective surface. So that's what we're talking about here. Okay, so let's look at some other methods in which we can get color in ceramics. All right, so I brought this up, and this is a particular crystal here that also has these color centers, and all color centers are their impurities or defects, which basically locally bond to an electron or holes. So those polarons that we talked about locally bond into electrons, right? And so those polarons can also be color centers. And so that's basically what we have here, is that we have a defect, so a fluorine vacancy, and that fluorine vacancy can bond to an electron if present, right? And so that's what we're talking about. So the way that we can actually get these is either by reduction. So we have an oxide that can be reduced, right? So multiple valence states. Or it can be from radiation. And I put this here as an example because this is something that we can actually see in the lab. So in 407, you didn't get to see this in person this year, but when we're conducting X-ray diffraction, again, source of radiation, sometimes what we see is that certain crystals, like this, or the glass slide that we actually use, can become colored from radiation. So essentially this spot that's purple here or yellow here, that's where there's a high concentration of radiation in the form of X-rays, and that causes these defects, these color centers, to emerge. And so that's another way we can get colors from these color centers, these defects. In the lab, so if you haven't watched the XRD video, I try to show this in the preparation of the glass slide, XRD slide. And so look for that. It tends to be a brown segment of the glass just like this. So it's not the powder, it's actually the glass slide itself. But those are what we're seeing, these color centers emerge in the glass. Okay, so that's color centers are another way we can get coloration. I also wanted you to think about another aspect of our lab, and that is the superconductors, the YBCO that we used in lab. And one thing you'll notice there is that those materials were either very dark or black. So some ceramics will turn black. And what I wanted you to think about there is the connection to visible light, right? So if something is dark or black, what that means is it means that the visible light is being absorbed and not reflected, right? And so if we think about that in terms of the band structure, that means that light that's either at or above the donator level, so we have an energy of light here, will absorb that energy and liberate an electron to the conduction band. And so that's something that happens when we have, so the dark or black color of ceramics can actually tell you something about the obviously optical properties, but also the electronic properties as well. So what that means is that as a very general rule, again, this is just a general rule that you can kind of apply to ceramics, is that when you see this dark coloration or black color in ceramics, this will typically tell you that this material is electronically conductive, right? Because it has electrons in the conduction band that are being essentially liberated as light is absorbed. So dark ceramics are typically electronically conductive. So this is just a general rule. I can't tell you that every single dark ceramic is conductive, but that's a pretty good rule to have. All right, and so the final aspect of coloration that I wanted to talk about was small metallic particles. So if small particles are dispersed in glasses, but also ceramics, this can cause scattering of light, and it also gives coloration. So a very famous example of this is a very rare and expensive antique, basically, to collect. It's called cranberry glass. And what this is, and why it's so expensive and rare, is because this is glass. These are the examples of cranberry glass up here that have gold nanoparticles, or small micro or nanoparticles embedded within the glass. So you can understand why it's so expensive with the gold. And those particles scatter and disperse light, and giving it this unique color with that same. Effectively, we're changing the wavelength of the light by scattering, by interaction with these particles, and so this gives us that red coloration after scattering.